Okay, let's have a look at problem 2282, number of people that can be seen in a grid. So here we are going to share a monotonic stack solution and make some connections with other problems. So this is a very common technique in doing such kind of problems. So first we will go through the statement of the problem. Then we will look at the idea and procedure and build intuition. And then we will write and explain the code. And finally we do some tests. So first let's look at the statement of the problem. So we are given an m by n theory indexed to the array of positive integers called heights, where heights ig is the height of the person standing at position ig. So next, basically the problem defines how one person can see another. So a person standing at position row 1 and column 1 can see a person standing at position row 2 or column 2 if, first, the person at row 2 column 2 is to the right or below of the person at row 1 and column 1. So second, everyone in between them should be shorter than both of them, so that they can the first people can see the second in the end. So the question requires to return an m by n to the array of integers. Let's call it answer, where answer ig is the number of people that the person at position ig can see. So these two items here actually are the key to a solution to this problem. So for example, let's first make a very trivial observation. So at position ig, we can only see from to the right and to the bottom. So that's a very trivial one. So here the problem provides two examples. Let's focus on the first one, because we can reduce the problem actually to example 1 in such a form. So here the height, let's comment, just focus on this first row, that is 31425. The answer is 21210 for this corresponding row. So the reason, for example, 3. So if we take this viewpoint, we see that 3 can see the nearby one. Every people can see the people next to him, so to the right or to the below. So 3 can see 1, and it can also see 2, person 2, that is height 4. So, but it cannot see 2 and 5 anymore, because they were all blocked by this person with height 4. So here is a 2. And so basically we can interpret all the items in the output. So this is example 1. So now let's look at the constraint. So the height and in other words, the rows can have a length up to 400. Similarly, the width also can have a length up to 400. And the last constraint is about the range of the height, which can be as high as 10 to the power 5th. So okay, with these constraints covered, let's look at the idea and the method. So the method we're going to use is called monotonic stack. So here we are actually using a decreasing stack. So the idea for this problem is simple. First, we just need to do work for generic row or column. So later we just use superposition. So let's focus on a row to fix the idea. So now we want to think in a reverse direction. That's the key of this solution. So at each index, we examine which persons before or to the left of I can see this person. Then we just do the update. So in the second step, for an index I, we should avoid doing whole traversal from the beginning to I. In other words, we should avoid using purely brute force, because this does not take advantage of the problem assumption. In other words, the two items we have emphasized before. So here comes the familiar monotonic decreasing stack, right? So here we will not specifically run the procedure. Let's first look at our change the viewpoint and look at the intuition. In example 1, just use row 1. So we have the height is 3, 1, 4, 2, 5, and the index are 0 up to 4. So we want to traverse this height, and in the process we update the initialization, which is initialized as all zeros. So for example, if we look at 3, because in 3 there's no people left to 3, the corresponding number here is still 0. And then if we look at index 1, so index 1, so the person left to it can see it, so we just increase that index position by 1. And then look at this index 4, so the people to the left, so this guy can see 4, we just update it by 1, and this guy can also see 4, we update another 1, so that's 2. So now let's look at index 2. So index 2, so this person can see 2, so we add 1. But all people to the left cannot see 2 because 4 is too high. It blocks all the previous ones, so we do not need to update anymore to the left. So now let's look at 5. So 5, so this person can see 5, so we're going to add 1 to it. And this 4 can also see this 5. Then we just add 1 to it. And all the people to the left cannot see 5 due to this 4. Therefore, for this index, we'll stop here. We do not need to check any further. The reason is that the last people in the row, or last people from top to bottom, the bottom people cannot see any people else. So this is the final state, 2, 1, 2, 1, 0. So we have 2, 1, 2, 1, 0. This is the intuition after we change viewpoint. In other words, at each index, we want to examine which persons to the left can see that person I. So we shall use decreasing stack to aid the above procedure. So in the stack, so essentially we are considering the height, but we will store the ID rather than the height so that we could update the initialization easily or accordingly. So that's basically the idea. So here, before we write the code and explain the code, so here are some challenges. First, can we try walking through the example below by intuition and by following the code we are going to write. For this height, let's see, this one, 10, then end at 9. So another challenge is, can we write a solution to Leetcode 1944? It's actually the same. So, or we can regard the current problem as an extension of problem 1944. So with that said, let's look at the code and write the code. And in the process, we are going to explain the intuition and the procedure. So for this purpose, first we'll write a helper function. So the helper function is that given an array, we are going to determine the number of people a specific index can see other people. So here I will define it as count visible. Let's see. So the input will be an array. Later, this array can be a row or can be a column. So for this purpose, I will first track the length of this array. But we can at the very beginning track the length of row or column. So, but it's okay just to make it isolated. So we have length is this, and we have result is 0 times length. So this is our initialization, right? So now we are going to iterate the array. So for I in range from 0 to length, right? Then we are going to do the following while loop. Well, s and array s the top is less than the current height. So because of this, we are going to pop. Due to this less equality, we are considering monotone decreasing stack, right? As the ones which is shorter than array I are going to be popped out. So what we have, we pop this then this means G, the people at index G can see person I. So then we are going to update this one by increment by 1. And that's about this while loop. So after this, what shall we do? We want to check if S is empty or not. If S still not empty, then the head element in the stack can see the person at array I, because the head now will be either higher or equal to this current person at index I. So what we want to do is that the result as -1, we're going to increment by 1. So now what we want to do is, if we check if array at this index is equal to array I or not. So if they are equal, what does it mean? It means the following. Let me write down the specific interpretation so that you can check later. So it means people shorter than this height at here, right, cannot see people after I, right? So this is a very easy interpretation. So intuitive, I would say people shorter than heights. Let's see, heights or array as -1, right? Cannot see people after I, right? So what's the reason? So this is the due to this is because the height I blocks, right? So for later persons, we just need to check from S -1 add to the right. So another note I want to make actually before we write the shortcode is that people left to S -1 can still possibly see people after I. So that because the people left to S -1 can be very high, right, very tall. So with that said, so if array S -1 equals this array I, we're going to update this top by I, right? So that we just need to examine from I onwards for later persons, right? So with that said, if we have set this one, we just continue. So otherwise, so for each one, so if at the very beginning, for example, there's nothing inside the stack yet, we're going to append or include this current index to the stack. So that's about the hyperfunction. So we're going to return the result. So this result will, given that at each position we compute how many people this people at the current position can see to the right. So with that said, we are almost done. So now let's look at the superposition for the grid, right? So this actually is rather routine now. So let's initialize a result which we are going to return. Then first I want to iterate for the rows and call this function. So for row in heights, so we just need to append so count visible result for the current row to the result. This will give us m rows in the result. Then we are going to consider a column. So each column we can regard it as a array or a row. So check column is actually easy. So we are going to use a zip function to do the matrix transformation equivalently. So for G and column in enumerate, so we want to use zip, use star heads. So this each column will correspond to something like 5, 3, 4 here. Then what we want to do is that we cannot directly update the result like in the check of rows, what we want to do is we first find the visibles, which we can call the function call visible, and apply to this column, and then we're going to update just one by one. For I in range, the length of the height, so this is how many rows. So then result I, j are going to be updated by visibles I, right? So that way we finished all the procedure. So finally we're going to return the result. So that's basically the solution, and in between we have tried to make connections with the intuition and the general idea. So this solution consists two parts largely. First is a hyperfunction which can be used to check the effect of each row and each column. And in the second step, we essentially do a superposition for the grid and to get the final result. So with that said, let's examine some special cases. So so here I didn't specify a S, so I'm going to initialize this S. It's running slow. So it passes the first case. Now let's look at the second second example. Yeah, it passes the second one. So now let's look at the generic case. Yeah, it passes the generic case. Yeah, I guess for this problem, here is a solution that can be used to solve problem 1944. So it's good to look at that problem. I guess that's it for now. Thank you.